Let us continue. Okay, so the question is the following. If I was able to reduce on AC, to reduce my system to one single force on AC, can I deduce what will be the location of the single force on AB? The answer is yes. Why? Because once I determine one possible point for which I can reduce the system to a single force, I can deduce infinite other points. Why? Because when you displace a force along its line of action, its moment about A will remain the same. Why it will remain the same? Because the perpendicular distance from A to the force will not change. And if you put the force here on AB, okay, since you have the same force magnitude and still the distance from A to this line will be always D, okay? So you will get exactly the same moment. That's why we say if we know one point of application for the single force, we can deduce infinite other points. But here, practically, we need point on the structure. So for this structure, you have intersection with line AB, so you can apply your single force somewhere on AB. So now, from the figure, you know already YA, okay? And you want to determine this distance, XA. How to relate YA and XA? I will draw a triangle here to show you, okay? You know that for this line, this is the line of F, okay? And F is decomposed into two components, FRX and FRY. Because you know the component FRX and FRY, you are able to calculate this angle, the angle of your line, okay? So you can calculate the angle or with the horizontal or with the vertical, both you can find them. So if you take this angle theta, you can say that theta is simply tan minus 1 FRX over FRY. And once I determine the angle theta, I can draw the following triangle. I can say that this distance is YA, that I already calculated, okay? The direction of the line of my force is doing an angle theta with the vertical. And what I want to find in this triangle is x of A. So this is x of A. So according to my geometry, this is a right triangle. In this right triangle, I can say that tan theta is equal to XA over YA. So from here, if I know YA, I can deduce x of A. So I can say that x of A is equal to YA times tan theta. And if we want to do analysis of this, what is the reason for this? Let us replace tan theta by its value. Okay, what is tan theta? It's FRX over FRY. So FRX over FRY is equal to XA over YA. And this is due to what? It's due to having same moment about A. Look, if I take YA to this side, what do I get? And XA to the other side. We get that FRX times YA is equal to FRY times XA equals to FRY times XA. And this is what? This is the moment. This is the moment about A. Okay. These two are equal to what? To moment, resultant moment about A. Okay. So all methods will give me exactly same results. All methods are based on when I want to have an equivalent system, I should have the same moment about the point. So if I displace on AC, only FRX will do a moment, and this moment MRA is equal to FRX times YA. And if I displace on AB, I have only the moment of FRY. So this is equal to FRY times XA. And I can relate XAYA or by this method, or also by saying that if I displace a force on its line of action, its moment about A will not change. So once I find one point of application for a single force, I can deduce all other points. Okay. Question on this? Okay. So let us continue. This is a typical problem, and you have a lot of problems of same concept to practice on this. So if we I will do other problem with other ideas. For example, this one. The following slab is to be hosted using the three slings shown. Replace the system of forces acting on slings by one equivalent force and couple moment at point O. The force F1 is vertical. This problem is, what is new in this problem is that I have 3D instead of 2D. Okay, and they just asked me to reduce at point O. To reduce at O, all I have to do is to find first F resultant. And to get F resultant, I need to find the expressions of F1, F2, and F3. And we have learned a lot, all methods together to find the expression of vectors. I can use unit vector, I can use angles, depending on what I know, okay? So now we'll look at our figure to try to find the expression for the different forces, F1, F2, and F3, okay? So to start with, I start with F1. F1 is vertical upward. So vector F1 is just 6K. Now I move to F2. Okay. For F2, I will zoom a little bit. Okay. You remember in class, we have seen together that one method to define a force is to project it first on a plane. Okay. Then decompose the projection on the plane to two components. This is the case here. So first, the first angle I need is this one. This is 45 degrees. How I will use this angle? I can say that for this angle, okay, which is 45 degrees, it will allow me first to determine this component, this one. This one. This represents actually what? This component is parallel to Z. So this will give me F2Z, okay? This is F2 in Z. F2 in Z is equal to 5 times sine 45. Okay? So I am done with the component along Z. I still have to find components along X and Y. So look, first, when I projected on XY plane, I need this angle. This angle will give me this length, this one, the projection on XY. I will call it L, okay? I will call it L, and this length of projection is F2, which is 5, times cosine the angle. So times cosine 45. But L is not X and is not Y. Okay, for this reason, they should give me in the problem another angle. And this angle can be or the angle with X-axis or the angle with y-axis. If you look at the figure, they gave you the angle between L and Y. Okay, so to have a clearer idea, I will draw it for you in 2D. If I draw it in 2D, what do I have? This is X. This is Y. And this is my line L. As you can see, if I consider my vector, it's pointing from this point towards the projection. It's backward, يعني I'm going in negative X like this. This is my vector. I'm going in negative X, positive Y, okay? And the length of this vector, the magnitude is L. And they gave me the angle this vector is doing with Y. If you look at the figure, they gave me this angle here with y-axis. This is 30. So when you draw the 2D view, it will be clearer for you. Okay? Now, you have L and you have the angle. Then you can decompose it into two components, one along Y. So since it's pointing in positive Y direction, we can say that F2Y is equal to plus L cosine 30 plus L cosine 30. Okay, so in total, what is F2Y? If I replace L by its value, it's 5 cosine 45 times cosine 30. While if I consider now X component, it's pointing in negative direction. So F2X is negative. So it's minus L times sine 30. So now if I replace L by its value, it's minus 5 cosine 45. This is L. And when I project it on X, I multiply by sine 30. So times sine 30. Okay. And now I was able to decompose F2 into three components. One along X, one along Y, one along Z. I am done with vector F2. I move to vector F3. What do I know about vector F3? I know the three angles. The angle it's doing with Z, the angle it's doing with X, and the angle it's doing with Y. And here they helped me a lot because no need to give me the three angles. They can just give me, if you remember, two of the angles. I can deduce the third. Just I should know in which octant I am. Yani for example, instead of giving you the angle with X, 60 degrees, they can just tell you this. They put a projection to show you, this is the projection point, to show you that F3X is positive. Since F3X is positive, then the angle is smaller than 90 degrees. So when you want to find F3, you say that F3 vector is equal. Let us call the angle theta, and we want to calculate it, theta. It's equal to F3, which is 4 in magnitude, times cosine theta in I plus cosine the angle with Y. The angle with Y is 60 degrees. 60 along J. Okay. Plus cosine 45 along K. Okay. Plus cosine 45 along K. Now, we just need to get theta, okay? To get theta, if they didn't give you the angle 60, you can find it because you say that I can apply the cosine rule. Cosine square of theta plus cosine square of 60 plus cosine square of 45 equals to 1. Equals to 1. Okay? And now from this relation, we can say that cosine square theta can be determined. Now we just have to select if we take theta larger than 90 or smaller than 90. So we look at the figure. If they tell us that from the figure, if they do the projection point here, this means that x component is positive. So I should select. Okay. Uh, Guys, do you hear me again?
Yes.
Okay. Okay. So we were saying that we can determine the angle, the third angle with x-axis just from the cosine square rule. Okay. And since the projection is positive, we select the value smaller than 90, which is 60 degrees here. Okay, but here to help you, they gave you already the three angles, but no need to give you three angles. They can just give you two angles and you will deduce the third. Okay, the only condition is to know if the projection on the axis is positive or negative. If the projection is positive, you take angle theta smaller than 90. If the projection is negative, you take theta larger than 90. Okay. Question on this first, how to determine the component of the three forces. Okay. Now, once you are done with the resultant force, you need to find, the question is to reduce at O. So because you want to reduce at O, what should you find? You should find the resulting moment about O. And now the only new thing here is that you have 3D. Because you have a 3D, it's easier to use the cross product. Okay? To start with, you should say that first, I have three forces. I need to get the moment of F1 about O plus the moment of F2 about O plus the moment of F3 about O. And for each one, we use the vectorial product. Here, for example, I can add also for you a couple to show you how to use it. And in addition to these forces, how we can have couples, we can have it in the following way. I will illustrate it for you in the figure. Okay, I can give you, for example, this symbol. Okay, if I put for you a vector. Okay, so how we can have a couple in 3D? In 3D, the couple is represented by a vector with an arrow like this. Okay, so whenever you see an arrow around the vector, this is a moment. And I can tell you, for example, this is a vector. The magnitude is 10 kilonewton meter. And you can know from the unit that it's a moment, but also we put an arrow around the vector to tell you that it's a moment vector. Okay, so please pay attention. If you have a moment vector, you don't consider it when you do sum of forces. You just consider it when you do sum of moments. So in addition to the moment of forces, moment of F1 about O, moment of F2 about O, and moment of F3 about O, if I put for you this couple vector M1, you add plus M1. And you deal with it as a normal vector. I can give you the component in X, Y, and Z, or I can give you the three angles, etc. It's the same method of any vector to define it. Or you know the components, or you know the magnitude and angles, or you know the direction unit vector, etc. So plus moment of couple. Here in the problem they gave us, no couples. Yani this term is 0. But in case you have in the figure a vector with an arrow, this is a moment vector. You account for it in in the summation of couple moments. Okay. Now, since we only have 3 forces here, we should add their moments about O. Of course, for F3, no need to do any calculation. F3 is passing by O, no moment about O. Now, for F1, you have 2 possibilities. For F1, you can use the cross product if you want. But since F1 is vertical, it's really simple to get F1 moment using another method other than the cross product. Because if you look at it, F1 is parallel to Z. So no moment about Z. Okay? To find the moment about Y, you do the right hand rule. If you put your 4 fingers like this, your hand along F1, okay? And the palm of your hand facing Y axis, your thumb will point into negative direction. Try to do it now. Try to do it, okay? Your thumb will point in this way, like this. So this is let me change the color. Okay. So your thumb is pointing in the opposite direction. Okay. 1 second. Okay. Look, I will erase this so you can see it in a better way. Okay. If you look at your force, put your 4 fingers along F. So if we illustrate it like this, okay, this is your hand, this is your 4 fingers, parallel to y-axis, okay, and the palm of your hand is looking towards y. Your thumb will point like this in negative y direction. So you can say that to calculate the moment of F1 about O, first, it's parallel to Z, yani no moment about Z. About Y, it's minus the magnitude of the force, which is 6, times what? The perpendicular distance. So look, if you do projection of your force, the perpendicular distance to y-axis is just 2 meters. And you need to multiply 6 by 2. Okay? This is along J. And you still have to account for the moment along X, along I direction. So now you should do the right hand rule again, but now you will turn your hand. You will turn your hand to be parallel to X axis, okay? And then if you do this, your thumb will point in positive I direction. Try to do it on your own, okay, with your hand. You will see that your thumb will point in positive X. So it's plus the magnitude of F1, which is 6, times the distance to X. And the distance to X is this one. This perpendicular will give you the distance to X, which is given to be 6 meters. So it's equal to 6 meters. So this is along I. And as we said, the force is parallel to Z, so no moment about Z. So now we got a moment of F1 in a simple way, F3 0 moment. We still just have the moment of F2 about O, okay? Now for F2, we use vectorial product. This is the easiest way, okay? So we say, let us call this point of application here of our force, let us call it C. So we have to do OC vectorial F2. So this is for MF2 about O, we said this is 0. For F3 because passing by O. For F2, it's OC. And you know well how to do the vectorial product, okay? You do the vectorial product and you get the moment about O. And now you add all moment of all forces to get the resulting moment about point O. Okay. So this is for the following problem. Any question on this? Here, they, instead of using the right-hand rule, they said, let me use for both F1 and F2 the vectorial product. It's right, you can do this, okay? So you can do whatever you want. All methods are right. You can use the right-hand rule, you can use the cross product, but sometimes the right-hand rule is easier. Yani look, you can, if you develop this, you will get exactly the same result of the right hand rule. Okay, so it's up to you, or you use the right hand rule when simple, or if you prefer to always use the cross product in 3D, you can do it also. Both methods will give you the same result. But whenever a force is complex, it has three components, of course the cross product will be much easier to use. Okay, any question on this? Please, if anything is not clear, I can repeat.
Can you please repeat the right-hand rule for the moment of F1 about O?
Yes, of course. I will draw it in a clearer way here. Look. Okay. You have, this is, let's say, x-axis. And this is y. And this is F1 here. Okay? Okay. So first you say the following. I have three axes. I have x, y, and z. And my force is only along z. It has only a component along z. So, and since it's parallel to z, can it produce a moment about it? No. So first you say for F1, no moment about z. Okay? Now, F1 can produce a moment about y and can produce a moment about x. To find these moments, you extend the line of F1, okay? And you find the intersection on XY plane, okay? They gave you that for this point of intersection with XY plane, you have distances. You have the distance here given. I will call it, let's say, let us go back to the figure. You can see it here. It's the 2 meters, okay? So this distance, the perpendicular to y is 2. And if you take the perpendicular to x, it's 6. So I will show it for you here. This is 2 meters. And it's perpendicular to y. Okay? And this distance, which is the perpendicular to x, is 6 meters. Okay? Now, you say, let me find the moment of F1 about this. I need the moment about O. And O is the intersection of X, Y, and Z. So first I can say that moment about O along Z is 0 because F1 is parallel to Z. I move now to moment about X and moment about Y. To get a moment about X, what should you do? Should multiply the magnitude, which is 6 kilonewton, by the distance to X. The distance to X is 6 meters. So you do 6 times 6. You still need to know if it's positive or negative, if it's pointing along positive X or negative X. That's why you need the right hand rule. To apply the right hand rule, you take the right hand and you put your 4 fingers, try to do it parallel to the force, okay? And the palm of your hand is parallel to x-axis. Then if you look at your thumb will point in positive x direction. So you can say that the moment is along positive x. So you can say that moment about the x-axis passing by O of F1 is equal to plus 6 times 6, okay, which is 36. Now, the moment about Y, you will do exactly the same procedure, but you will revert your hand, yani you will rotate your hand in a way to have your hand now parallel to y-axis. Try to do it, okay? If you do this with your right hand, your thumb will point in negative y like this, okay? So you can say that the moment of F1 about y-axis, okay, is equal to minus, because your thumb is pointing in negative direction, minus the magnitude of the force, which is 6, times the distance, which is 2. And now if you want to write it as a vector, what can you say? The moment vector of F1 about O is equal. What is the component along I? The component along I is MOX. So it's plus 36 in I. Okay? Now, along Y, you have a negative moment. So minus 12 in J. And since you don't have any component along that, so it's plus 0 along K. Okay? Clear?
Yes, thank you.
Any other question? Okay, guys, thank you. And sorry for the connection issues. Bye-bye.